My name is Michael Pont. In this video, I'm going to provide an introduction to the use of time-triggered, or TT, software architectures in safety-related embedded systems. I'll begin this presentation by explaining what a TT software architecture is. I'll then go on to look at how we can model systems with a TT software architecture and how we can monitor systems with such an architecture at runtime. I'll go on to consider why you might wish to use a TT software architecture in your next safety-related product. I'll explain the difference between a TT system and a TT wrapper. And I'll explain the difference between a TT system and the use of a conventional real-time operating system. I'll give you some suggestions where you can provide further information about the topics presented in this video, and I'll then present my conclusions. The techniques presented in this video have been used in a wide variety of different safety-related systems. Some of the related standards are listed on this slide. They apply in aircraft systems developed according to DO178C, DO254, automotive systems developed in compliance with ISO 26262, household goods developed in compliance with IEC 60335 and IEC 60730, industrial systems developed in compliance with IEC 61508, machinery systems developed in compliance with ISO 13849, medical systems developed in compliance with IEC 62304, and space systems. The technique can also be applied in a range of other sectors. So let's begin at the beginning. What is a TT software architecture? This is the definition that we're going to use in this video. When saying that an embedded system has a time-triggered architecture, we mean that it executes at least one set of tasks according to a predetermined schedule. The schedule determines the order of the task releases, the time at which each task is released, and whether one task can interrupt or preempt another task. So this is what a time-triggered system might look like. We have some tasks being released according to a predetermined schedule here. Task A followed by task C, followed by task B, followed by task D. The task sequence then repeats. So these tasks might be implemented in your program. Each task might be implemented as a C function, and it might be released by a very simple scheduler framework that we'll talk about in a few minutes. So in practice, the usual starting point for a TT design is a bare metal software platform. There's no RTOS, no real-time operating system, no Linux, no Windows. That's what we mean by a bare metal platform. The starting point will be one active interrupt per CPU. Just one active interrupt per CPU, usually linked to a periodic timer tick. And we're going to poll the peripherals on this design. So my goal in this presentation is to explain why this is a good starting point for many safety-related embedded systems. So let's look briefly at how we might begin to construct such a system. So we might have a simple code framework illustrated on this screen. So in our main loop, so this might be sitting in our main loop, we simply put the processor to sleep. The main operation of the system is controlled by a 1 millisecond timer tick here. Whenever that timer tick is generated, we have an interrupt, and that interrupt is linked in this simple example to a single function called update. Within that function, we might call some tasks or functions, possibly by means of a long switch statement. And this is sometimes called a very simple time-triggered system with cooperative tasks. In practice, we probably wouldn't build the system this way, certainly not for a safety-related system. In practice, we'd use some kind of simple task scheduler. And this would give us a cleaner way of adding tasks to the system with an appropriate interface. I'm not going to discuss in this video how we would create a task scheduler. If you're interested, you can find further information about that, for example, in the Patterns for Time-Triggered Embedded System book. I'm not trying to sell you this book. You can download this book, about 1,000 pages, free of charge from our website. And you'll find complete information there about how you can build a range of different schedulers for use in various simple TT systems. So our system at the end of the day then, regardless of the kind of scheduler etc. we use, is designed to release tasks according to what's usually called a tick list. In practice, the system will probably have multiple operating modes, and in each operating mode we may release different tasks depending on the requirements for the application. For example, in this aircraft design, we might have a different set of tasks that are used while the plane is leaving the runway. We might have a particular set of tasks while the aircraft is cruising in level flight, and we might have a different set of tasks that's used while the aircraft's coming into land. The key thing here, crucial point of this, is these task sets in each of these operating modes, the task sets are predetermined and can be analysed at design time to ensure that they provide the required behaviour. So if you like, these task sets are themselves static. They're checked and carefully analysed at design time. But crucially, the transitions between task sets may happen at random times. So of course we don't have to assume that there will be a transition between tasks 10 minutes after we leave the runway, etc. What will happen is the transition between tasks is effectively event triggered. But the task sets in each of the operating modes can be carefully designed and verified at design time. This approach doesn't just apply to single processors. In many cases there may be multiple processors, or there may be multiple cores on a single ASIC. Let's assume we have multiple microcontrollers connected together, and we're going to create a larger time-triggered system. So we might connect these systems together using a CAN bus, RS485, SPI, FlexRay, whatever, as our communication bus in this distributed system example. On what we will call the master node, we have a timer. Let's assume that's generating periodic interrupts every 10 milliseconds. Every time an interrupt is generated on that master node, the master node is going to send a message. Let's assume it's a CAN bus. We'll send a message on the CAN bus. The arrival of that message at the slaves will drive the scheduler on the slave nodes. In this way, we can synchronize the activity that's carried out on the master node with the activity that's carried out on the various slave nodes in this network. So we can synchronize the activity across multiple CPUs. These microcontrollers that we're synchronizing the activity on, they may be on the same PCB, or they may be at opposite ends of a factory or in different parts of a vehicle, for example. It doesn't greatly matter. We can synchronize the activity across multiple processors very easily using this kind of time-triggered design. We're not simply talking about cooperative tasks. We can create time-triggered systems that are fully preemptive, so that we can have various levels of task priority and tasks can interrupt one another. As we'll see shortly, one key difference between this kind of preemptive design and a conventional RTOS is that the design in this case can be rendered completely immune to priority inversion. We'll say a little bit more about that in a few slides' time. So the key advantage of TT systems, the first key advantage is that we can model the system behavior very precisely at design time. So this becomes what's sometimes called a semi-formal development process. So we represent our system in each operating mode by what is known as a tick list. Now we looked briefly previously at a graphical representation of this tick list. In practice, the tick list will probably be represented as a text file that looks something like this. In this simple design, this represents the entire hyperperiod. That is, the interval before this set of periodic tasks begins to repeat itself. So the hyperperiod runs task A, task C, task B, task D, and then the task sequence repeats itself in this design. Once we have the tick list for our system, we can do key things. We can model precisely what the system response time will be. For example, we can model how long it will be before an emergency stop switch is pressed and a robot begins its shutdown process. We can model the level of task jitter, that is the variation in the release time for any of the tasks in the schedule. We can also model the maximum CPU load for the system. Let's just look at one of these examples. There's a typical requirement in many designs that will be to specify what the maximum CPU load will be. This may be a requirement that comes in from your customer, for example. In a TT design, we can work out exactly what the maximum CPU load is by checking each tick in the hyperperiod. So here, for example, let's assume this tick interval between here is 10 milliseconds. So we have periodic ticks generated every 10 milliseconds on this processor, we assume. And we're running these particular tasks in the tick interval. Let's assume this represents the whole hyperperiod before the task sequence begins to repeat again. In this case, we simply go through the whole hyperperiod and sum up the maximum task execution time for all the tasks that are released in each tick interval, and that gives us a representation of the maximum CPU load. So we're looking for the tick in which we have the maximum task execution time, and that reflects the maximum CPU load for this design. It's important to appreciate that this is fundamentally different from the average CPU load calculation that's carried out in many systems. And often there's an enormous difference between the average CPU load and the maximum CPU load. And in practice, all we really care about is the maximum CPU load in the majority of safety-related systems. A TT design allows us to calculate this. Let's look at one other issue that's a side effect of using a TT design. Often projects change. It's an inevitable factor in most projects. You very carefully drop the requirements at the beginning of the project, but the requirements inevitably change as the project progresses. So the kind of question that we might need to ask then is, can we add an additional task to the system without having an impact on the existing task set? And in a TT design, the answer to that question is often yes. So here, let's assume this is our representation of our existing task set. We could add into this schedule an additional task X, in this case, into the sequence. Doing this would have no impact on the existing tasks in the set. So we could do this late in the day in our project without having a significant impact on the other tasks in the project and without changing the results that we had obtained from previous integration tests on the system. This is extremely useful and extremely valuable in many projects. When it comes to runtime behavior, we can then make use of our models to allow us to monitor the system. So let's just take the larger picture here. So I've just touched on, very briefly summarized the fact that TT designs are easy to model. For example, we can represent the maximum CPU load, the response times, and the jitter for the system. But these models are necessarily based on a number of assumptions. So I'm assuming we have an operational CPU in each microcontroller. We're running the correct program on each microcontroller. We have an operational scheduler on each microcontroller. We can transfer data between tasks on the same microcontroller without corruption. We can transfer data between microcontrollers without corruption if we have more than one microcontroller in the design. We have operational peripherals on each microcontroller. We know at least the worst case execution time and possibly the best case execution time of all tasks on each microcontroller. And we know the execution sequence of the tasks in each operating mode on each microcontroller. In a TT design, we can incorporate mechanisms that will test all of these assumptions at runtime. And then we can react in a precisely predetermined way if these assumptions are not met. Again, this is extremely powerful. So we are able to incorporate extensive self-monitoring capabilities into the system so that we can detect if anything has happened at runtime that suggests the system cannot meet the requirements. Let's just look at one example of this kind of runtime monitoring. Suppose we've got a design with two microcontrollers in it that might be used to meet IEC 61508 requirements, for example. So we have two microcontrollers in this design and they're performing cross-checks between them continuously during the operation of the system. In this type of design, we might have microcontroller A configured to run the tasks shown above. So microcontroller A is supposed to run task A, task C, task B, task D. We would then in this design configure microcontroller B to check the task sequence from microcontroller A before each task is released. This is the crucial part. So in this time-triggered design, we're storing a separate independent representation of the expected task sequence on a second microcontroller. And before microcontroller A releases a task, for example, before it releases task B, it will check with microcontroller B to ensure that task B is due to be the next task that's released in the schedule. If that's not the case, typically we would shut the system down, but other behavior will be more appropriate in some applications. The key here is that this is predictive monitoring. Just imagine that, for example, task D releases the airbag in an automotive application. In this kind of design, we can double check before we release the airbag that this is an appropriate action that we should be performing, and we increase our confidence that the airbag will only be released when it's appropriate to do so in the application. This is very powerful. This form of predictive monitoring is very powerful and it can only be achieved in a time-triggered design. So, why should you consider using a TT software architecture in your next safety-related product? Let's take a step back again from this. I'm suggesting you should use no RTOS. I'm suggesting you should not use Linux and you shouldn't use Windows, and you should use a bare metal platform making very limited use of interrupts. For many organizations and many developers, this just looks like sheer insanity. This is not the way that most people are taught or self-taught to develop embedded systems. However, it's perhaps not quite as mad as it looks at first sight. You may be familiar with the MISRA-C coding standard, and you may be aware that for many organizations, use of the MISRA-C guidelines is a key requirement for many safety-related systems. we can view MISRA C as a safer subset of the more general C programming language. And this idea of using a safe subset or a safer subset of a programming language is widely recognized and widely employed in safety-related systems. Let's consider a more general situation at the architecture level rather than at the programming level. At the architecture level, event-triggered systems, which have multiple interrupt sources and may employ a conventional RTOS, they're a general class of systems. A time-triggered system can be viewed as a safer subset of this kind of event-triggered architecture. One of the reasons why TT designs are popular is because they have highly deterministic timing behavior. In this slide, I illustrate one of the challenges that it can apply in any sampled data system. For example, a control system, a condition monitoring system, digital signal processing, etc. Let's take a very simple example. Suppose we wish to sample a 500 Hz tone using an 8-bit analog to digital converter. This is not a high-end requirement. This is a very modest requirement. We can do the calculations and demonstrate that the maximum allowed jitter we can tolerate in that data sampling will be approximately 1 microsecond. Even for an 8-bit ADC and a 500 Hz tone. If it's a 24-bit ADC, for example, the requirements are much, much tighter. So the maximum allowed jitter we can tolerate is about 1 microsecond. Any more jitter than that in your application and the system will not necessarily operate as expected. Effectively, once you get to 1 microsecond, effectively we have a 7-bit ADC. As the jitter level increases, the ADC resolution is effectively reduced, 8-bit, 7-bit, 6-bit, and so on. As a general rule of thumb, if we've got more than 10% jitter, so 10% of the required sample period jitter, it means that the data are likely to be absolutely meaningless. And it's not generally possible to reconstruct the data that we've lost in this kind of design. This basic requirement, this basic timing requirement applies both at the inputs and at the outputs of control systems. And the impact of this is, in my experience, often completely underappreciated or not necessarily understood by many developers who use more complicated software architectures such as an RTOS. So one of the advantages and one of the reasons why TT architectures are employed is it allows us to have very precise control of timing behavior for key tasks when this is required, and that can allow us to control jitter in a manner that can often be very useful in many data monitoring, data acquisition, control applications. One of the consequences of this is that in the influential international safety standard IEC 61508, use of TT architectures is highly recommended for systems at safety integrity level 2 or above. Static synchronization of access to shared resources, which is a key characteristic of all TT designs, is recommended at SIL 3 and highly recommended at SIL 4 in IEC 61508. Limited use of interrupts, a defining characteristic of TT designs, is recommended for SIL 1 and SIL 2 systems and highly recommended for SIL 3 and SIL 4 systems in IEC 61508. So let's now turn our attention to the difference between TT systems and TT wrappers. So far we've looked at time-triggered software architectures. These can be employed in TT systems or in TT wrappers. In a TT system, a TT software architecture is employed in all MCUs, all of the microcontrollers. And the microcontrollers will usually be qualified. For example, they might be SIL2 qualified or ASIL-D qualified. Sometimes this is expressed as SIL2 ready or ASIL-D ready, for example. So that's a TT system. Everything is time triggered. Another important class of system is a TT wrapper, which is used to monitor what's usually called a target system. So in this type of design, the TT wrapper employs a TT software architecture, usually running on a qualified microcontroller. The target system that we're monitoring will not usually employ qualified components. This is another powerful combination. So you can, for example, use a TT software architecture in a TT wrapper and integrate that with a system that uses a conventional RTOS or potentially uses Windows or Linux, for example. I'll give some examples of both TT systems and TT wrappers in the course of the next few slides. So for the TT systems, we're going to look at controller for a domestic washing machine, an industrial monitoring system, a steering column lock controller for a high volume passenger car. Look at how we can use TT systems in high reliability space-based designs. We'll look at a controller for an industrial robot, and we'll look at a machinery example where we can try and determine that the operator of the machinery is in his or her seat. We're also going to look at TT wrappers. First example we'll look at is for dealing with what's called SOUP, software of unknown provenance, in a medical application. We'll look at the development of a controller for an autonomous road vehicle, a self-driving car, using a TT wrapper, and we'll look at the use of TT wrappers in civilian aircraft systems. So let's start with the TT system examples. The first example we consider is a controller for a domestic washing machine. At heart, a washing machine consists of a powerful electric motor enclosed in a metal casing. As part of the normal device operation, the electric motor is used to rotate a heavy metal drum at high speed. Access to this potentially dangerous mechanism is controlled by a door with an electronic locking mechanism. The door lock is our key consideration here. If the door lock fails or the door can be opened during normal operation, then it's possible that a child in particular could open the door and gain access to the heavy rotating drum. This could be very damaging, potentially even fatal for a small child. So this type of control system needs to be developed in compliance with international safety standards IEC 60730 and IEC 60335. In such standards, this would be considered to be a Class B design, a safety-related design rather than a safety-critical design in this case, in that failure of the system would not lead directly to an injury. It would require, for example, failure of the door lock and someone opening the door for the possibility of an injury to arise. If, for example, we were controlling something like the central heating boiler, a central heating gas boiler, for use in a domestic environment, that might be considered a Class C design because failure of that boiler control system could lead directly to a gas explosion and directly to loss of life. In the case of our washing machine, this is a Class B design. It's safety related. We could probably develop this quite happily using a single microcontroller running a time-triggered software architecture as illustrated on the screen here. We call this a correlator platform. It includes mechanisms for checking the task sequence, for checking the task execution time, and it also includes support for an internal watchdog timer. So there's a single microcontroller in this example running a TT software architecture, and this is our first TT system. Next example we'll look briefly at is part of an industrial monitoring system that might be used, for example, to sound an alarm if, say, a gas leak is detected on an industrial site. Here we're assuming that this part of the system is connected, for example, over a CAN bus, to the rest of the industrial monitoring system. So we're concerned in this example only with the sounder unit. So our software architecture would be very similar to that which we used in the washing machine in the previous slide. The difference here is that we've also got an external watchdog device. So if this microcontroller fails, then the external watchdog device will kick in, and it will ensure that the sounder unit in this device cannot be activated if this microcontroller fails. That would be an important consideration in this type of design, because false alarms coming from one or more of the sounder units in an industrial facility would be likely to reduce the faith that the people in the facility have in the alarm system, and it could mean the next time there is a real alarm, they ignore it, and there are bad consequences from that. So this part of the industrial monitoring system would be developed in compliance with IEC 61508 at SIL 2 level, and could be done quite happily using a single microcontroller and external watchdog device running a time-triggered architecture. The next example we'll consider is an automotive design. In this example, we're considering the locking mechanism that's used to lock the vehicle, to secure the vehicle when it's left, for example, parked in a car park. So we're controlling here a locking bolt that is inserted into the steering column when the vehicle is locked. We're doing this development in compliance with ISO 26262, and this will be a top-end ASIL-D design for ISO 26262. The key hazard that we need to avoid here is the possibility that the locking mechanism could fail and attempt to lock the vehicle while it was in use. For example, while the vehicle was in use on a motorway driving at high speed, if the locking mechanism was engaged and the vehicle was locked under these circumstances, this could clearly have severe implications for the passengers in the vehicle. In this design, we're assuming that the system can be put together using a single microcontroller and an external watchdog device. This time we're using what we call a decompositor platform. This supports what's known as ASIL decomposition in ISO 26262. So in this case, we have a single TT scheduler, and we have two independent sets of tasks, both running on the same microcontroller. So in this example, we have an ASIL-D design, and we would have two sets of ASIL-B tasks running in this system. Next example we'll look at briefly is a space-based system. So in this design, the challenge is a little different. There are no immediate safety implications in, for example, a satellite control system under most circumstances. So in this case, our particular goal is to try and ensure that we can pick up any potential problems in the system and improve the system reliability. So in this design, for example, we might use two processors and perform cross-checks between them. If we detect any discrepancies in this time-triggered system, we would reset the system in a controlled manner and hope that this would deal with the problem. This is likely to be an effective solution in our space system because one of the main sources of problems is likely to be single event upsets that might cause disruption to memory in our system. Memory and register contents in our system might potentially be disrupted in this way. And the use of our dual time-triggered architecture would give us a means of addressing these challenges. Other applications of dual processor designs are many industrial control systems. Designs developed in compliance with IEC 61508 often require use of two processors with cross-checks between them to meet hardware fault tolerance requirements. This is an illustration of a dual processor design connected over a single communication bus to a programmable logic controller, a PLC in this case, and is used to control, we assume, a small industrial robot. So we're using two processors in this design, synchronized processors using shared clock architecture to ensure that we can safely control this industrial robot. A related design might be in compliance with ISO 13849 at PLE level. In this case, we're assuming that in this design we need to ensure that there is an operator in the cabin of this vehicle before the device can take any action. So we're ensuring that there's an alert operator in the cab of this piece of machinery before we will allow the machinery to be operated. And we're doing this using two low-cost camera modules fed into two microcontrollers with a time-triggered software architecture. Gives us a simple, highly robust means of meeting the ISO 13849 requirements. So this meets one of our requirements for a designated architecture in ISO 13849. Let's now briefly look at some examples of TT wrappers. In this example, we're considering the control of a medical infusion pump. So this medical infusion pump might be used, for example, to provide drugs to a patient who was undergoing treatment for cancer. We need to ensure that the correct drug dosage is provided to the patient. We have here a processor running what's known as SOUP. This, according to International Safety Standard IEC 62304, is software of unknown provenance. So we have a processor here that's generating the signals that we would wish to use to control our medical infusion pump. This is running unqualified software. For example, the target processor in this case may be running an RTOS, Windows or Linux. End result is that we have outputs coming from this processor that are unqualified, and we cannot be confident that these outputs are correct. Therefore, we cannot directly feed these outputs to our medical infusion pump. Instead, what we do is we take a TT platform, a TT wrapper, running on a qualified processor, on qualified processor hardware, and we use this platform using what we know as a correlator B platform. We implement a TT wrapper, and we use this TT wrapper to check the validity of the outputs that come from the processor running SOUP. This is a powerful approach. It can apply very effectively in medical systems developed in compliance with IEC 62304. This is another example of the use of a wrapper in a safety critical embedded system. So in this design, we're looking at an automotive design developed in compliance with ISO 26262, again at ASIL D. So what we're assuming here is that we've got an autonomous road vehicle controller, an ARV. And this is, we assume, considered to be QM software. So it's not qualified software, it's not ASIL rated software in this ISO 26262 design. It might, for example, include a neural network. It might be taking the sensor inputs, applying a neural network algorithm, and working out the required speed and direction information for the vehicle. So we have sensor inputs here, possibly coming from a LiDAR, a radar, visual sensors. We're feeding them, this information is being fed into our ARV controller, and that's generating speed and direction information. But at this point, the ARV controller is not running qualified software and is probably not running on qualified hardware. So we're going to use a TT wrapper again, this time again ASIL D software running on an ASIL D qualified processor platform. This will be a small component here. This software is likely to be complicated. This hardware may well be complicated with multiple cores, etc. This software will be comparatively simple. It's typically going to be a dual-core lockstep processor running a simple TT software framework. This wrapper will be responsible for two things: for performing sanity checks on the speed and direction information that's obtained from the controller, and also for performing test injection between sensor frames on the ARV controller. The end result is, using the TT wrapper, we get the confirmed speed and direction information from our ARV controller, now in a form that we are more confident in the safety of this design. Final TT wrapper example we'll look at is in civilian aircraft systems. When developing modern aircraft systems, typically these days off-the-shelf processors are used, which are not aerospace qualified. This is now almost inevitable. Then the market, if we compare the number of processors that are required, for example, in civilian aircraft with the number of processors that are sold for use in automotive applications, the automotive applications are 1,000 or 1,000,000 times as many probably every year as the number of processors that are required in aircraft systems, because comparatively small numbers of aircraft systems are produced. So we now have off-the-shelf processors rather than custom aerospace processors used in many civilian aircraft. And we are required to have a safety net mechanism around such processors to ensure that they can operate safely in compliance with international standards DO178C and DO254 in this domain. So in this case, we're assuming that we can use a TT wrapper made up of some appropriately qualified microcontrollers to implement an appropriate safety net mechanism for wrapping up the outputs from these commercial off-the-shelf processors. So the TT wrapper examples that I've looked at very briefly in this presentation have all so far involved the following combination: some kind of target processor running unqualified code, probably on unqualified hardware, combined with a TT wrapper, probably running on a unqualified hardware, certainly running on a separate processor. And the end result is our goal is achieved, that we create a qualified embedded system. There's another possibility that we've also worked on over recent months. Many organizations these days produce ASICs, application-specific integrated circuits, for use as part of, for example, an automotive system. These ASICs are assembled using various IP blocks, silicon IP blocks. Some of these blocks will be qualified, other blocks will not be qualified. The end result we want to achieve is we want to have this whole ASIC that contains these various IP blocks, we want to have this qualified. And in particular, we want to be confident that this ASIC will operate correctly. We can do this by incorporating a TT wrapper mechanism within the ASIC itself rather than as a separate processor. And this can be an effective way of ensuring that our ASIC will meet the required requirements. So next, I'd like to consider briefly the differences between a time-triggered and an event-triggered system, and consider in particular the difference between the use of a TT system and the use of an RTOS. So as we've seen, event-triggered architectures are a general case, and TT systems can be seen as a subset of a more general case of the use of event-triggered architectures. The main way that event-triggered architectures are implemented these days is through use of a traditional real-time operating system. So a typical event-triggered design will be required to handle multiple interrupts. So the developer may employ a task to handle these events directly. This could involve creating an interrupt service routine to deal with each event. The developer may also choose to employ a conventional real-time operating system to support the event handling. Whether an RTOS is used or not, the end result is the same. This event-triggered system must be designed in such a way that task releases, which may occur at what are effectively random points in time and in various combinations, are always handled in compliance with the system requirements. This can be challenging in an event-triggered design. The main benefits of an event-triggered architecture are that they're familiar to many developers. They have a faster response to random events than is generally possible with a TT design. They're supported by various RTOS products, and they're considered to be easy to build. There are, however, some significant challenges. For a non-trivial design, there may be a large number of possible system states in an event-triggered system. Because, for example, suppose we have 10 interrupts enabled, there are lots of different combinations of the ways in which those interrupts, which may arrive at random points in time, can be processed in different combinations. Priority inversion cannot be avoided in an event-triggered designs. We can reduce the effects of priority inversion, but we cannot eliminate it. I'll say a few more words about that in a few minutes. We have to consider timing behavior, the jitter of periodic tasks, because this will be less predictable than it is in a TT design. We also have to consider the fact that any changes to the design are likely to require a full suite of regression tests, because it is difficult to predict what the side effects of any changes will be. Overall, we generally need to operate the system at around 50% CPU load to allow some overhead. And it can be difficult to scale up the system to work with larger tasks. 20 plus tasks or so starts to become very challenging. This is because, again, of the state explosion problem. The more tasks, the more activities we have on the system, the more difficult it is to be sure that we've tested every possible combination of states before we ship the product. If we haven't done this, then we can have a combination of state in the field that has not been predicted at design time and is not handled correctly. This can have catastrophic consequences. Let's just look briefly at the question of priority inversion. In my experience, some organizations, even if they consider this at all, don't fully understand the implications of priority inversion in event-triggered designs. So let's just look at a simple example here. We've got 5 tasks, we assume. A, B, C, D, and E. The highest priority task is task A. The lowest priority task is task E. We assume that we've got some shared resources here. So we assume, for example, in this design initially, that task A, task B, and task C all require access to an ADC unit. They're probably using different channels in the ADC, but we assume they all require access to the ADC unit. So let's assume further that the system is running, the tasks are triggered effectively at random times, and task C is using the ADC unit when task A wishes to use it. So task A is the highest priority task, and we would hope that task A would always have access to the ADC when it requires it. In an event-triggered design, when the tasks are triggered at random times, we don't know when task C will require access to the ADC, so we have to accept that there are likely to be circumstances in which task C, for example, is using the ADC when task A would wish to use it. So we have to use something like a ceiling protocol to promote the priority of task C while it is using this shared resource in order to reduce the impact of priority inversion on this design. Correct use of a priority ceiling protocol, for example, will help to address this problem, but it won't solve it completely. All that the priority ceiling protocol is doing is ensuring that task C completes its access to the ADC as quickly as possible. It doesn't mean that task A, the high priority task, gains access to this resource when it requires it. Of course, you may decide that you wouldn't create your design in such a way that you had multiple tasks accessing an ADC. You might decide that only one task would access the ADC, obtain the data from the ADC, and pass this to another task. This doesn't directly solve the problem. It changes the problem, but it doesn't directly solve it. What we end up then with is more shared data, and we still have the challenge of accessing these shared data in memory. It still gives us the same priority inversion issues. If we turn this into a TT design and consider the priority inversion again, the problem doesn't arise. As in the TT design, we know in advance when, for example, task C and task A and task B are going to require access to this shared resource. So if we wanted to do a runtime check in our TT system, we could do so. So if a runtime check would look something like this. So C, before it accesses the ADC, would ask the scheduler, may I access the ADC now? And the scheduler would either say, yep, go ahead, use the ADC, or the scheduler would say, no, you can't use the ADC because there's a high priority task due to execute in 30 microseconds. It will require access to the ADC, so you'll need to wait to ensure that the high priority task gains access to the ADC when it needs to do so. And that's effectively the behavior we can implement. It's easier to implement than it is to explain in a TT design. Essentially, because the task sequence is scheduled in advance, we can completely remove the problem of priority inversion in a TT design. So we render it immune to the problems of priority inversion in a TT design. So if we look at TT more generally, it's widely recognized as providing an appropriate platform for safety critical systems. This is because it's easy to verify that the system will operate according to the specification, because it's immune to priority inversion, because the scheduler has very low CPU load, because high CPU loads can be supported safely, for example 90%, which gives us very low unit costs because we can make efficient use of the processor, and TT scales up even to extremely large systems. Because the behavior is deterministic, we can always work out what the impact will be of adding a new task. The main challenges for TT designs are for those used to ET designs. Time trigger designs can seem to be more difficult to build. I meet many organizations who seem to feel that all they have to do to create their safety related system is take a qualified processor, take a qualified RTOS, throw a few tasks at it, and the system will be fully qualified. Unfortunately, the process is a little bit more complicated than that. But ET designs look much simpler to build. The main technical challenge with a TT design, once people understand how to construct them, the main technical challenge is that the response times, which are carried out by polling, will be fully deterministic, but inevitably these will be slower than for an ET design. So if you need response times to random events of less than around 100 microseconds, you probably won't be able to use a pure TT design, and you'll need to consider using a quasi-TT design instead. So a quasi-TT design involves including additional asynchronous interrupts in a TT design. If we have only 1 to 2 additional asynchronous interrupts and short interrupt service routines, then the impact on the design will be limited. Nonetheless, this must be conducted with care. If you're going to monitor your quasi-TT design, which you'll need to do if it's going to be a safety-related system, you can continue to monitor the TT tasks in the manner that we've discussed previously. We can monitor the execution time of the tasks, and we can monitor the task sequence of the TT tasks. This process will be the same as we use in a pure TT design. For the event-triggered tasks, we would additionally monitor the ISR execution time, and we would probably monitor the interval between event-triggered ISRs. Both of these would allow us to have increased confidence in the correct operation of our quasi-TT design. I hope some of what I've said in this brief presentation has been of interest, and now I'm just going to look at some places where you can find some further information about the use of TT, software architectures, TT systems, and TT wrappers. We have about 7 hours of free introductory training videos that explain the use of TT systems available on our website, and you'll find the URL here on the bottom of the screen. You'll also find our PTTS book. This has about 1,000 pages. There's numerous code examples that go with it. Again, you can download this free of charge from our website at the URL shown below. You may also like to consider our ERES2 book that was published in 2016. This provides further information about the use of TT systems and has a particular focus on the use of TT systems in safety-related products. You can find further information about this book and some sample chapters at the URL shown at the bottom of this page. If your organization is interested in developing safety-related embedded systems using TT architectures, we'd be very pleased to help. We offer a range of safety solution packages that are designed to help your development team produce a safety-related embedded system quickly and cost-effectively in compliance with one or more international safety standards. Our packages are, of course, based on TT software architectures and include carefully selected combinations of our various products and services. The URL on this screen will take you to a page that provides a great deal of further information about these solution packages. So that brings us towards the end of this presentation. This is what I'd like to ask you to do, please. When you next start the development of a safety-related embedded system, please encourage your development team to ask the question, could we build this product using a TT software architecture? I think you may be surprised how often the answer is yes. And if you use a TT software architecture, then, in my view, you will see very many benefits to your system development, and you will be able to have increased confidence that your system is likely to be safe. You'll find further information about TT systems on our website. The URL is on this page. Thank you very much for watching this video.